Assalamu alaikum everyone. So today we will be talking about cellular wireless networks and we will be going through lecture number 28. So during this course we talked about a lot of different ideas, techniques and topics, right? So we started from transmission media and we discussed different media type, their characteristics, and then how we actually decide about the media type depending upon our infrastructure, our requirement, right? So for example, we have two different types of media, guided and unguided media, and those different type of media, they have different metrics. For example, they support different bandwidth. They can be used for targeting, or by targeting certain objectives to be achieved during the communication from one point to another point. So our objective is to transmit data from one point to another point. So of course channel media is always there. So we have established different media types, their characteristics, their impairments, right? And then we also categorized different media on the basis of guided and unguided media. And then we, of course, when we talk about the communication, so it's not an easy task. So you have to transmit data from one point to another point, right? So it's a very complicated task. So when there are a lot of different systems that are involved, right? A lot of different impairments that we have to come across. So what we did to simplify this task, we chunked down that complicated task into smaller subtasks, right? So in that way the complication is also divided into steps, right? And we have adopted layered approach. So when we talk about the protocol, so actually the protocol is the layering of those different subtasks, right? So at each layer we have a different subtask that has to be performed, and the ultimate goal, ultimate objective is the data transmission, right? So we have talked about different protocols and the layered approach, and we have also discussed why we need layered approach and what are the protocols, and we also talked about TCP/IP stack, that is actually a bunch of protocol. And then after that we talked about antenna. That is a very important component of wireless communication. So then different antenna types and the characteristics those different antenna types they are providing, and then the propagation, that is also very important when we talk about the antenna, because antenna has to receive energy in the form of electromagnetic radiations from free space, right? When it is receiving, or when it is a receiver, acting as a receiver. And on the other side, if we talk about the transmission, so it has to transmit or radiate energy, electromagnetic energy, into the free space whenever it is acting as a transmitter. So though nowadays we have antennas that can play both transmitter and receiver role, transceivers, so they are actually transceivers. And then of course when we talk about the data communication, so for example I have to transmit a JPEG image, or I have to transmit an image, simply an image, right? So in order to transmit that image from one point to another point, there are a lot of different steps that are involved. So first, source encoding, right? That is actually the representation of the data into a certain format, right? In order to transmit it errorless, in order to have errorless transmission, right? So if we talk about the still image, so there is the data that is redundant for us. For example, it is not visible by human eye. So why I should be transmitting, first storing, then carrying, then transmitting that data from one point to another point, and that is redundant data for me. So I want a source encoding scheme so that that redundant information should be thrown out, right? So source encoding and then channel encoding. So I want to make that data compatible with the underlying channel that I'm going to use. So source encoding, channel encoding, and then after the channel on the receiver side, right, I will be doing all those steps in reverse order, right? So we have talked about different source encoding and different channel encoding schemes. Then of course when we talk about the data communication, so we have to come across, we have to face certain errors. So we should be able, or our system should be capable of detecting errors first and then error corrections. So there are certain schemes, encoding schemes, that provide both error detection and correction. And we talked about different, started from simple, for example, parity, which can detect error up to certain extent, right? So it has its own limitation. When then we talked about some other NRZ and some other error detection schemes. So some of these schemes, they have the capability to detect and correct error. So we talked about different error correction and error detection and error correction schemes. And when we talk about the communication, for example, if I'm trusted to communicate data from one country to another country, from one Pacific to another Pacific, right? So if the distances are very high, on the higher side, right? So in order to have communication, I need antenna or a tower to an enormous site, right? So for example, in maybe hundreds of kilometers or thousands of kilometers, right? That is not possible and that is not feasible. And this is required due to the curvature of the Earth. So we talked about how we can overcome this difficulty, and we discussed satellite communication. So we can launch a satellite, although the launching is not an easy task. So all the countries, or they don't have the capability to do so, but we can have, we can buy different transponders, and we can buy bandwidth from satellites that are owned by some other country. So we talked about the satellite communication, and by having satellite communication, we can transmit, or we have data communication, or communication from one country to another country, from one Pacific to another Pacific. So we can cover larger area, right? So for example, the ground station should be transmitting data to the satellite, and satellite, because it has a bigger footprint, it have a bigger coverage area, so it can transmit to another ground station, to another part of the world. So we talked about the satellite communication. Now we will be utilizing most of the concepts, most of the techniques which we have studied so far, and we will be applying them during cellular wireless networks. So these are the bullets which we will be going through one by one. First of all, principles of cellular network. Then the objective is to raise the capacity, to have error-free, error-prone communication, to reuse the frequency. That is a very precious resource, right? So in order to do that, we need to divide the area into smaller cells. So in order to do that, we will be talking about cellular geometries. For example, we can have square geometry, hexagon geometry, right? And the objective is to reuse the frequency. For example, in one cell, we are using a particular frequency, and we can reuse the same frequency in another cell, but not the neighboring cell. Then, of course, our objective is to raise the capacity. And there are different techniques and different methodologies, and by using those methodologies, we actually can increase the capacity of the underlying cellular communication. And then if we talk about on the broader scale, so we have macro cells and then micro cells, right? So small cells, and then if we bundle those different cells, right? So we can define a macro cell. And then there are certain operations that has to be performed when we talk about the cellular system. For example, I want to establish a converged infrastructure where the fixed telephony lines and the mobile telephony infrastructure, they are converged, right? So I can initiate a call from fixed conventional PSTN line, and I can call the cellular or mobile telephone, and on the other side, if I want to call from mobile set to the fixed line, so I can do that. So we have to go through different steps, different operations in order to achieve this goal. Then, of course, there are certain stages when we talk about the call within the cellular network. First, we all know that whenever I want to make a call from my cell phone, so I dial the number and then I press the call, then I have to wait for a certain amount of time. So that is actually the call setup time. And after the call is established, then the actual data starts flowing. So we have to go through, though we we cannot even realize that what's going on behind the scene, but we need those different steps in order to establish the call setup, and then after the setup, the actual data starts flowing. Then design factors, when we are talking about the design of a cellular system, so we have to take into account certain design factors. So we will be talking about different design factors. So after that, the impairments that we cannot escape. Whenever we talk about the communication, wired or wireless, so we have to face those different impairments. So we will be talking about those impairments and their solutions, how to overcome those different impairments. Then finally, we'll be talking about how cellular communication actually started, first generation, and then there is the improvement. Actual first generation started on the basis of analog, and then they enhanced and they have shifted to the digital, and finally now the improvements are a process, continuous process, right? So we have third generation, and nowadays we can say that we are living in the fourth generation or maybe the fifth generation. So we will be talking about those different points in detail. So let's talk about principles of cellular network. So the idea was to increase capacity for mobile radio telephone service, right? So we want to raise the capacity, because if we look or talk about the old radio telephony, so we have a very limited capacity, right? Provided by one high power. So we need very high power transmitter receiver, right? And you can imagine that it can only support 25 channels, right? So due to the high power, the area it can cover, it's on the higher side. So we have a radius of 80 kilometers. So you should remember 25 channels, but we have to provide very high power transmitter and receiver, and the radius is about 80 kilometers. So here we will be talking about the cellular network organization, right? So based on multiple low power transmitters, we divide the area into smaller cells, right? In maybe a square pattern or hexagon pattern, right? Each cell has its own antenna, right? And each cell is actually dedicated a range of different frequencies, right? And in each cell, we will be having a base station that is actually having transmitter, receiver, and the control unit, right? So we have a base station, right? And that base station is actually capable of handling different frequencies or frequency ranges, right? So there are a lot of antennas that can be mounted on to that base station, and we can have transmitter and receiver separately, or maybe we can have transceiver. Then of course we need a control unit right, in order to control all the underlying communication. So that is done by, again, base station. So if we talk about the neighboring cells, they actually use different frequencies to avoid crosstalk. So one frequency or one range of frequencies for one cell, and the neighboring cells are using different frequencies in order to avoid the crosstalk. Okay, so here are the cell geometries. So you can see on the left-hand side of your picture, we have a square pattern, and on right-hand side we have a hexagon pattern, right? So if we talk about this square pattern, right? So you can see if I'm focusing over here, right? So this plus sign. So you can see that we have, if I suppose that we have antenna here, base station here, base station here, and base station here, right? So the base station antennas, they all are equidistant from this antenna. So if a user is here, right, so it is very easy for this base station to make the decision that the user is going to register with which base station, or if the user is moving, then again we have to decide that which base station should be used, right? So first design decision to make is the shape of the cell, right, to cover an area, right? So here you can see that we can cover an area D if we talk about this plus sign, and if we talk about this cross sign, so we can cover an area of 1.414 D, right? So this area is a bit bigger than this plus area, right? And then matrix of square cells would be the simplest, as you can see that in case of a square cell, we can have a simplest layout to define, right? All the antennas in this case, all the antennas of neighboring cells, right? So for example, if I focused on this, right? So this is the central square, and all the other squares, they are neighboring squares. So all antennas of neighboring cells are equidistant, right? So as mentioned, those antennas that are lying along the plus and the antennas that are lying around the cross, they are equidistant, right? So in this way, this configuration actually simplifies the task of decision making when a mobile user move within a cell, right? So for example, if the mobile user is moving from here to here, right? So actually we are approaching towards this antenna and we are moving away from those different antennas. So it's easy for the base station to take the decision that which antenna should be used, right? So let's talk about the hexagon pattern. So so you can see, if I consider this as the focus, as the center, right? So you can see that now we have all the antennas. So this is the center of the individual hexagon. For this hexagon we have this center, right? And for this hexagon we have center here, and so on and so forth, right? And here, and this is the center for this hexagon, right? So now you can see that all the, if I suppose that the base station is situated here at the center of each hexagon, so all the antennas, they are equidistant, right? So D and D and C. So what I can do, if I have to draw a circle, so I can draw a circle, right, in this way, and the radius of this circle will be same. Okay, so see, what is the objective of this cell geometry, right? So the ultimate objective is to reuse the frequency. For example, we will see that if we are using a certain frequency over here, right? So we will not be going to use this frequency here, here, and here, and all the neighboring cells in order to avoid the crosstalk. So what we'll be doing, right? So this is a very simple division or pattern. So we can have a lot of different scarce cells. So if we have a scarce cell here nearby, right here, for example, this is the right. So now if I'm using a particular range of frequencies over here, so I can reuse those frequencies over here, right? And if I'm using a particular frequency over here, so I can reuse those frequencies over here, right? So the objective is to share nearby cell frequencies without interfering with each other. So what is the advantage? It allows multiple simultaneous conversations, 10 to 50 frequencies per cell. So you can imagine how we can effectively and efficiently use frequency resource, right? So power of the base station, base transceiver, control, allow communication within cell on given frequency. So it limits escaping power, right, to adjacent cells. So now here the question is that how many cells must intervene in between two cells using the same frequency without interference, right? So before we have very simple configuration over here. So now we have a bit complicated configuration over here. Frequency reuse pattern for n is equal to 4. So you can see 1, 2, 3, 4, right? Circle with radius d, right? And here you can see we have n is equal to 7, 1, 2, 3, 4, 5, 6, 7. And again here, black cells indicate a frequency reuse for n is equal to 19, right? So if I have to count, so n is equal to 19, right? So the ultimate goal is to reuse frequency patterns. So here let's define few parameters. D, minimum distance between centers of cells that use the same band of frequencies, and they are actually called co-channels. R is the radius. So for example here we have a radius, right, of a cell, right? So as mentioned over here, we can define the radius of a cell. D, distance between centers of adjacent cells. D is equal to R, right? So adjacent cells, for example, this one and this one, and n number of cells in a repetition pattern. Each cell in the pattern uses a unique band of frequencies termed as reuse factor. So here reuse factor is 4, 7, 19. So you can see 1, 2, 3, 4, 5, 6, 7, and here 1, 2, 3, 4. So this is actually the reuse factor. So let's talk about a scenario where the number of users that belong to a particular cell increases, and as a result the traffic also rises on the higher side. So what we can do in order to resolve this situation? So we can take frequencies from the neighboring cell and allocate those different frequencies for the time being, right? And we can also have cell splitting, non-uniform topography and traffic distribution, use smaller cells in high use areas, right? So we can also use cell splitting, and frequency borrowing is also take frequency from, or we can borrow frequency from adjacent cells by congested cells, right? Okay. So here is the cell splitting. So to use a small cell power, must be reduced, right? So of course the cell power must be reduced to keep the signal within the cell, right? So here is the we can have another mechanism for increasing capacity, cell sectoring. Cell divided into wedge-shaped sectors, 3 to 6 per cell, each with own channel set, right? Directional antennas at base station, right? So we can use directional antennas, for example, 1 degree, and we can sector that cell into 120, 120, and 120, right? So 3 to 6 cells. Microcells, as cell becomes smaller, antennas move from top of hills and large buildings to top of small buildings and sides of large buildings, right? So as the cells are becoming smaller and smaller, so we don't have to raise the antenna to high-rise building, and of course the power will also be reduced. So use reduced power to cover a much smaller area. And this configuration is good for city streets, roads, and inside of large buildings. So here we will be talking about typical parameters for macrocells and microcells, right? So here we have cell radius. So for a macrocell, you can see the area is on the higher side. We can cover 1 to 20 kilometer, and for microcell, we can cover from 0.1 to 1 kilometer. And in order to accommodate macro cell, we need more power, transmission power, because the area is on the higher side, so 1 to 10 watt. So here the area is on the smaller side, so we need less power, 0.1 to 1 watt. And this is good for cellular or mobile communication, because our handsets, they don't have enough batteries. If we have to use the same cells, mobile cell phones which we are using nowadays, so our battery will be depleted very fastly when we talk about having communication in this macro cell. And then the average delay, of course, 0.1 to 10 microseconds. So for microcell, 10 to 100 nanoseconds, right? So here maximum data rate, bit rate, 0.3 megabit per second, and here we have 1 megabit per second. So the data rate is also on the higher side for the microcell. So if we talk about the frequency reuse example, so here we have different configurations. You can see over here, right? If we talk about the left-hand side picture, right? So you can see that if I have to calculate the height, right? So remember that the cell radius is 1.6 kilometer, right? So 1.6 kilometer. So have to calculate the height, right? You can see height is equal to 5 into 3 under root into 1.6, right? So I can calculate the height by using this formula. And remember, 1.6 is cell radius, and if we talk about the width over here, right? So you can see that 11 into 1.6, right? So how this 11? So let me 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. In order to take this width into account, because each cell has a radius of 1.6 kilometer, and you can see that if I'm here, right? So you can the difference, right? And if we talk about this, right, this configuration, so here we have a smaller cells, right? So you can see the cell radius is half now, 0.8 kilometer, and the width now becomes, right? So again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, and 21. So in order to calculate the height, so I can again count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So here you can see 10 into 3 under root into, because cell radius is 0.8, so multiply by 0.8, so the height becomes 139, so this is the area. And if I have to calculate the width, so I have to take, right, 21 into 0.8, 16.8 kilometer. So here we have mentioned the operation of the cellular system. So you can see that we have mobile telecommunication switching office, MTSO, and base transceiver. Base transceiver, actually they actually are connected with the MTSO, and here we have the PSTN, that is the conventional telephony network. So all the base stations, they are connected to MTSO, and the users that actually are in a particular cell, they are connected to the underlying base station, right? So the idea over here is, if a user it has to call from this PSTN line to this cell phone, right? So then it has to be connected, this PSTN, there should be some call termination, right? It can be hardware or maybe a software or maybe both, right? So then the call will be switched from PSTN to this cellular infrastructure, and then cellular infrastructure will route the call to the corresponding base station, and then this will be again forwarded to this cell phone that is called party, right? So if we talk about the communication from cell phone to this PSTN line, so base station will be sending or connecting with this MTSO, and then MTSO will be sending, while looking at the number, it will realize that this has to go for this PSTN line, and it will route the call and forward the call to this conventional PSTN infrastructure. So there should be a specialized hardware. So we can also have another solution, that is because the switches are required over here, so we can use asterisk, that is with some specialized hardware with some TDM card, in order to terminate this PSTN lines onto the cellular infrastructure, right? So there are a lot of different solutions, right? So here, channel, two type of channel between mobile unit and base station, control channel and the traffic channel, right? So let me explain that what a control channel is and what the traffic channel is, right? So by we have isolated the control channel from the traffic channel, right, in order to make the process more simpler. So whenever I have to call, for example, from mobile telephone to another mobile telephone, mobile set, right? So first of all, I will be assigned a control channel, right? So that is, you can say, for signaling. So the base stations, MTSO, and the all other devices that are involved in call setup or signaling, they will be sharing certain data in order to have the call setup. For example, if we talk about the endpoint, so they will be talking about, for example, codec, what sort of codec is being used, the capability and capacity of the endpoints, and there are a lot of different parameters that has to be decided during the call setup, during the signaling, right? And then after the call is set up, right? So actual data has to be start flowing, right? So in order to have actual data flowing, we have to use the traffic channel that is actually carrying the actual data, voice or data, or maybe something else, right, or maybe video. So we have control channel, set up and maintain call, establish relationship between mobile unit and nearest base station. So whenever I'm talking about the control channel, so whenever I will switch on my cell phone, so you can see that before I can see the signals that okay, I'm registered, or I have the signals from my carrier, so there's a delay. So during this delay time, the cell phone and the corresponding base station, they are actually communicating with each other. For example, the profile of the user has to be loaded, and the user location has to be recorded for billing, and there are a lot of different steps that has to be taken in order to have a user registered for a particular cell. And this and after that we are actually, so here are the call stages, right? So we will be talking about the call stages, different call stages, right? So here strongest signal, for example, mobile unit initializes, you have turned on your mobile set and it scans that, for example, it is here and it is scanning that which base station is providing the maximum signal, the power of the signal, right? And of course the power for this base station, right, is maximum because it is very close to this base station, and if we talk about those different 3 base stations, they are too far, so the signal are weaker from those base stations. So as a result, this user or this cell phone will be registered with this base station, right? And then of course, if now the user is registered, its location has been noted, and there are some other parameters, for example, profile, the authentication, authorizations, they all are loaded, right? And now if the user want to make a call, right, so request for a connection, we talk about the B. So as this base station is connected to this MTSO, right, so the mobile user will initiate the call by sending, right, so of course it has to dial some number, so let me, okay, so it is here, so it has to dial a number. So after the number is dialed, it will be, the information will be sent to MTSO via this base station, that is the native base station for this mobile user, because this user is registered with this base station. And then what the MTSO will be doing after request for connection, it will be perform paging, right? So it attempts to complete the connection to the called unit, right? So depending upon the called number, so it knows that this number can be for this base station, so depending upon the number, it will be it will be sending paging messages to different base stations, right? So remember that it will look at the number that is dialed or called, and depending upon the number, it will be sending paging messages to different base stations, right? And in the 4th step, that is D, now the corresponding base station, it replied to MTSO, okay, the user is with me, right? So now send me more information, right? And the call mobile unit recognizes its number, right, on the setup channel, right? So call is accepted over here, right? And here we have the ongoing call scenario. So those 2 different mobile users, they are connected via the corresponding base stations, and this is MTSO that is supervising this communication, right? And if this user has to move from this cell to this cell, right, so in that case, of course, you can see that the power will be decreasing, cell power will be decreasing when the user will be moving here, and here at the edge of this cell, right, or you can see maybe can realize that the power is becoming weaker, right, and it has to switch, right, from this cell to this cell. So in that case, a handoff should be performed, right? So we can have different handoffs, for example, vertical handoff or horizontal handoff. So here, as we are talking about the same technology, right, so we assume that it is a horizontal handout, and this BTS will be contacting this BTS via MTSO, and then there is a huge there are a number of steps that has to be performed before the actual handoff, right? So they can also perform the handoff, and there can other functions that we can have when we talk about the cellular communication. Call blocking after repeated attempts. So we normally come across, we can experience this if all traffic channels are busy, a busy tone is returned. Call termination, so when a user hangs up, so of course the resources are allocated when the call is set up, so those resources has to be freed formally, right? So when a user hangs up, channels at the base station are released, call drop. So when a base station realize that it cannot maintain the required strength of the signal that is required in order to in order to maintain the communication, so it can drop the call. Call to from fixed and remote mobile subscriber. So here is the convergence. It can also perform the functionality of call to from fixed and remote mobiles, right? So here are some of the mobile radio propagation effects, right? So signal strength, strength of the signal between BS and mobile unit needs to be strong enough to maintain signal quality. So as mentioned, if it cannot maintain the required signal strength, the call will be dropped. So this is, and not too strong so as to create co-channel interference. So it should be not too strong that it is creating interference for the and must handle variations in noise, fading, time variation of received signal, and we can also have fading can also be caused by changes in transmission path. Signal strength is in effective range, signal propagation effect may disrupt the signal, right? So we can have fading because different signals, they arrive differently, and here are some of the design factors that we have to take into account when we talk about the cellular infrastructure, cellular communication, right? So desired maximum transmission power level at BS and the mobile unit, right? Typical height of the mobile unit antenna, available height of the BS antenna. Here are the propagation effects, right? Use model based on empirical data, widely used model, right? That is by some of the individual, right? So these are the design factors, propagation effects, right? Desired maximum transmission power, typical height of mobile unit antenna, and available height of BS antenna, right? So here we can use those different experiences that they actually have after collecting the empirical data. So here we have the multipath propagation. So you can see that here important propagation mechanisms: reflection, scattering, diffraction, right? So you can see refraction here, diffraction here, and here we have this spectrum. So let's talk about diffraction. Direction or intensity of wave at the edge of a noise of an obstacle, right? Because the RF signals slow down as it encounters the obstacle and causes the wavefront to change direction, caused by buildings, small hills, and other, right? Okay, diffraction at the edge of an impenetrable body that is large compared to the wavelength of radio wave, right? So this is large, this object is large as compared to the wavelength of the radio wave, So as a result, we have a diffraction. So you can see diffraction is occurred here. Scattering, when RF signal strikes an uneven surface, causing the signal to be scattered, are less significant than the original signal, right? So you can see we have a scattering, and we can also see multiple reflections, right? Multiple reflections over here. Multipath propagation, right? So transmitted power pulse, transmitted pulse, right? So receive line of sight pulse. So here you can see the effect of multipath propagation. So whenever a mobile unit moves down to a street in an urban environment, rapid variations in signal it occurs, right? So let me define over here. So this is the signal, for example. So as time, right? This is the power. So as we know that this signal, it is composed of different frequency components. Different frequency components. So those different frequency components, so let me, different frequency components, they will fluctuate differently. So as a result, we can have fading, right? So the variation in signal strength, right, occurring over distances about 1/2 a wavelength, right? So we can have different type of fadings, fast fading, rapid changes in strength over half wavelength distances, then slow fading, slower changes due to user passing different heights, high gaps in buildings, then flat fading, all frequencies in same proportion simultaneously. This is flat fading, and then selective fading. Different frequency components affected differently. So if we talk about this signal, so it is actually composed of different frequency components. So different frequency components, they are affected differently, and here the all frequency components, they are affected in the same proportion, that is flat fading, here selective fading. So as we know that errors has to be there, so we should be applying some error correction, error detection and error correction mechanisms, right? So we talked about different error correction schemes, right? So let's talk about error compensation mechanisms. Forward error correction, applicable in digital transmission applications. Ratio of total bits to data bits is 2 to 3, right? So adaptive equalization we can also have applied to transmissions that carry analog or digital information, right? So we can apply this mechanism to analog and digital information. So it is used to combat intersymbol interference, intersymbol noise, dispersed symbol energy back together into its original time interval. So we can have another error compensation mechanism, that is diversity, based on fact that individual channels experience independent fading events, use multiple logical channels between transmitter and receiver. So we use logical channels between transmitter and receiver, send part of the signal over each channel, right, and doesn't eliminate noise but reduces. So this mechanism does not eliminate noise or errors, but it has the capability to reduce the noise, right, or errors. Space diversity involves physical transmission paths, more commonly refers to frequency or time diversity. So spread spectrum is one example, right? First generation analog cellular communication. So original cellular telephone network, that was actually the first generation was actually based on telephone cellular network analog traffic channels. So it was deployed in North America, right, by AT&T, and the name was Advanced Mobile Phone Service, AMPS, also common in South America, Australia and China. And then it was replaced by second generation. So here we have some of the parameters that are taken from AMPS base station transmission band, 869 to 894 megahertz mobile unit transmission band, right? And here spacing between forward and reverse channel, that is important, 45 megahertz channel bandwidth. So you can see the bandwidth 30 kilohertz, full duplex voice channels 790, and here mobile unit maximum power 3 watt. It's on the higher side, and cell size, it's again 2 to 20 kilometers. So the technique that is used for modulation, FM, you can see modulation and modulation control channel. This is for voice channel, because we have voice communication only during the first generation. So for the control channel, the modulation scheme was FSK, frequency shift keying, and the data transmission rate is 10 kilobit per second. So it's again on the lower side. So there is an error control scheme, right? So capable phone has numeric assignment module, NAM, in read-only memory, number of phone, serial phone number of phone when phone turned on, transmits serial number and phone number to MTSO. Okay, MTSO has database of mobile unit reported stolen, right? So this is you can say this is the plus, right? MTSO uses phone number for billing, right? So phone number is used here for billing purposes, used in remote city services, still billed to the user's local service provider, right? So billing is unique. It's based on, so here is the call sequence. Subscriber initiate call keying in number. So MTSO validates telephone number and checks user authorized to place the call. So here the authorization and authentications are validated over here, and then issues messages to user's phone indicating traffic channel to use, right? So its channel is allocated over here, and ringing signal to the call party, to the recipient party, and then one call party answers, and then a circuit is established between the calling party and the call party, and one party hangs up, the resources are free, or circuit is free, and it is available to be used for the next call. So here we will be talking about AMPS control channel, 21 full duplex 30 kilohertz control channels, and they are used in order to transmit digital data using FSK, frequency shift keying, and the data is transmitted actually by using frames, right? So control information can also be transmitted over voice channels during conversations, right? Because there has to be control information that should be flowing during the ongoing call, ongoing voice communication. So control information can also be sent, can also be transmitted over the voice channel during conversation, right? So mobile unit or the base station inserts burst of data, right? So we can also have the handoff facility, right? And then here we have the second generation, that is actually CDMA, provide higher quality signals, right? Higher data rates, right? And support for digital services. And there are some key differences: digital traffic channels, encryption. So now we have more security, error detection and error correction scheme, which we don't have in the we have only error. We go here, error control coding. So here we have error detection and error correction scheme, channel access, and we are using multiplexing techniques that are TDMA and CDMA, right? Okay, so here let's talk about the multiplexing scheme that is used in the second generation cellular networks. CDMA, code division multiple access, have a number of systems, IS95 using CDMA, each cell allocated frequency bandwidth, in 2 half for reverse channel and the half for the forward channel. And we are actually using direct sequence spread spectrum, orthogonal chipping code in order to provide multiple access. So let's talk about CDMA. Allows multiple users to transmit over the same wireless channel using spread spectrum. Each user uses a different spreading code. The receiver picks up one signal by matching the spreading code. Okay. So features of the CDMA multiplexing technique used with spread spectrum. Given a data signal rate D, break each bit into K chip according to a fixed chipping code. Resulting new channel has chip data related rate KD. Chips per second can have multiple channels superimposed. So here we have the example. This is the code user A. It's a code for user A. This is the user B, right? And this is user C. So you can see different codes for different users, and this is the message 1101. It has to be encoded by using those codes, right? So this is the modulation, data from user 1, data from user 2, data from user N, and here we have different codes, right? And this is the modulation, and then the signal is transmitted, right? And this is the transceiver block, software in code generation, right? Local code generation, and this is the hardware, right? We will not, here we have the example. So we just have to multiply 1 into 1, right? So simple maths is involved over here. So here we have the actual signal, and this is the high bandwidth spreading code, right? So you can see this is the high bandwidth spreading code, and this is the low bandwidth, right? So signal is spreaded onto the frequency band, right? So you can see that low bandwidth and high bandwidth code, this will be repeated again and again, and we have the resultant over here. See, mix is, right? 1 1 1 1 minus 1 minus 1, right? So we will be multiplying this and transmit to decode, because this is the encoded signal. We have to use the same code, and here you can see that after having the same spreading code, and this is the original data we got after decoding, right? Okay, so wideband CDMA parameters, channel bandwidth 5 megahertz, and structure, channel structure, direct spread, chip rate 3.84 mega chip per second, frame length 10 millisecond, slots frames 15, and we have this is the modulation scheme that is used for WCDMA, quadrature phase shift keying and binary phase shift keying. This is for reverse. For forward we use QPSK, for reverse we use BPSK, right? And then we have the other parameters. So here we have some of the advantages of CDMA. Frequency diversity, noise burst and fading have less effect, right? So multipath resistance. So CDM is more prone to multipath fading, and then privacy, because it's very secure. If some of the jammer or eavesdropper they want to tap or jam, so they will not be able to do that, right? So more users mean more noise, and more errors lead to slow signal degradation until unacceptable, right? Self-jamming, right? So unless all of the mobile users are perfectly synchronized, transmission from multiple users will not be perfectly aligned on chip, boundary, thus the spreading sequence of the different users are not orthogonal. So we can have self-jamming. We can also have near for problem. So here you can see we have our rack receiver. This is binary data and code generator. They are XORed here, and this is the modulator. And you can see that we have different copies of the signal, and they are delayed differently, right? And here are the different multipath factors, and we have combined them and transmitted them onto the channel. And here is the demodulator, right? And on the receiver side, cover the signal by correlating the chip sequence, right, over here with dominant incoming signal. The remaining signals are treated as noise, but even better performance can be achieved if the receiver recovers the signals from multiple paths, right? So from multiple paths, we have multiple paths over here, and then combine them with suitable delays, right? So you can see suitable, we have tau 1, tau 2, and tau 3, right? So again here, more explanation of RAC's receiver. Again, original binary signal to be transmitted spread by the exclusive OR. This is the spreading code, right? And this spreading code with this binary data, we are actually using spread spectrum, right? Or as you can see, chipping code. Sequence is then modulated. Here is the modulated, right, for transmission onto the wireless channel, right? Channel generates multiple copies, right? So here multiple copies are replicated, right, with different delays, right, tau 1, and different attenuation factors. These are attenuations, right? Receiver combined signal is demodulated. The demodulated chip stream is then fed into the multiple correlators. These are correlators with different delays, right? These signals are then combined using weighting factors, right? So these are different weighting factors in order to receive the. So here we have IS95 second generation CDMA scheme, North America. Transmission structures are different on forward and reverse links. So some of the parameters, right? Forward links, so pilot channel synchronization and paging, and here we have the forward link processing, right? Scrambling, power control. So we are using direct sequence spread spectrum, right, which we already have gone through. So here comes the third generation cellular infrastructure. So it actually is a high-speed wireless infrastructure that support multimedia, data, and video in addition to voice, right? So now we have more services that can be supported in 3G infrastructure. So here are some of the features of the 3G. We have the voice quality that is comparable or very close to the PSTN and available to user over larger areas. So we have higher data rate, right? And then we can also have higher speeds for office uses, right? And symmetric and asymmetric data rate. So you can switch accordingly if you need more bandwidth for the downlink or maybe more bandwidth for the uplink. So we can it can be accommodated accordingly. So one of the main feature over here is that we have packet switching and circuit switching. So that's why we are able to support a lot of different services over this 3G infrastructure due to packet switching and circuit switching. They are merged together, so we can offer different services. And then adaptive interference to internet, and then more efficient use of available spectrum. And there are a lot of different technologies and services that are being introduced in 3G. So these are the driving forces when we talk about the 3G. So there are a lot of different objectives and requirements that are involved in the launching development of 3G. So the actual trend was going towards the converged sort of communication. So we want an infrastructure where all the services, for example, data, video, voice, and multimedia services, they are converged onto a single platform. So 3G actually support all the services that are converged, right? So we have convergence, and then we have another, that cellular telephony with SIM, that is subscriber identity module. That is also one of the requirement when we talk about the GSM cellular communication. The personal communication services, PCS, and the personal communication networks, right? Digital, using time division multiplexing access or core division multiple access, right? So, and here we have the typical mobile device capacity demands, right? So feature phone, right? Applications phone such as the Motorola Razr are used primarily to make calls and texts. They have limited web activity with a stripped down web browser, right? So we have a web browser that don't have a lot of features and functionalities that a conventional browser have. Usage during online session, voice call 4 MB per hour, web browsing 4 to 5 MB per hour. Average monthly capacity requirement 100 MB, right? So if we talk about the smartphone, right? So it has now the BlackBerry or some other smartphones. Now they are actually have web browser with more features. Again, data is on the higher side, and superphone, right? So it's more advanced device like iPhone than tablet. iPad greatly increased capacity. Web browsing, right? So we have more data accommodation over here. So that's I think terrestrial radio alternative interfaces. We have direct spread, right? Multi-carrier CDMA and time code CDMA signal single carrier TDD and frequency time, right? DACT. So they are CDMA based, and here we have TDMA based. Those so we can think about Thuraya, that is a phone, satellite phone, right? Bandwidth and chip rate. So these are the design considerations for CDMA, right? Okay, so here we have the 4th generation. So enormous requirement for data traffic, right? Or for wireless networks, more terminals accessible to the internet, permanent connections to the email. So we need permanent connection to the email, multimedia services, support for real-time services, for example, HDTV or maybe real-time multimedia. So based on the use of orthogonal frequency division multiple access, OFDMA, there are 2 strong candidates, right, for 4G standardization. One is LTE, long-term evolution, and the second one is IEEE 802.16, right? Okay. So here we have summed up the cellular network generation, wireless network generations, technology, design, right, and then implementation, 1G, 2G, 2.5G, and 3G and 4G, right? So if we talk about data rate, right, so you can see the enhancement, 1.9 kilobit per second, 14.4 kilobit per second, and it's on the higher side. And here we have the, theoretically, we have 200 megabit per second. If we talk about the schemes, multiplexing schemes, for 3G we have CDMA, and for 4G we have OFDMA, right? So for core network, it's for 1G core network is PSTN, right? That is circuit switching network. So here for 2G core network is PSTN, again circuit switching. So 2G is totally based on circuit switching, and here we have the packet switching and circuit switching, right? So 3G is core is on packet networks, and for 4G we have the IP backbone over here. So here we have mentioned some of the advantages of OFDM. Right, so fading does not affect the whole signal, and we can overcome the inter-symbol interference in multipath environment. Equalizers that are very complicated component, right? So it's not necessary to deploy equalizers. Some subcarriers, not the whole signal, right? So more important, overcome inter-symbol interference ISI in multipath environment, right? OFDM quadrature phase shift keying that is being used for OFDM, right? So here we have the okay, so that's all for today's talk. So today we talked about principles of wireless cellular network, and then the operations of wireless cellular network, and then we talked about the different generations of wireless, first G, 2G, and 3G, and then 4G. And finally, we have talked about different techniques that are being used in those different generations. So that's all for today's lecture. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफिज़. अस्सलाम वालेकुम.